EC 111 Lecture 3, Set 6, Simulation and Synthesis. What we've learned so far is that the System Verilog HDL can be used for both simulation and synthesis purposes. In this class, we'll be using in particular two different software packages. One is a Model Sim Simulator, which has a user interface. It could be interfaced to many different design options. We are interfacing it to an Altera FPGA design in this class. It could be interfaced to application-specific designs as well. After we have got this design done in simulation, we go and we synthesize it on the real piece of hardware. And the tool that we use for that synthesizing into real piece of hardware is an Intel Altera Quartus Prime. And these two are both essential in making designs, because we cannot make a big design before we simulate it. We cannot make a physical implementation of it. And physical implementation assumes that we've taken care of the design earlier in terms of testing and verification at a higher level. So typically, this Model Sim Simulator not just has a System Verilog code, but also has test benches and uses part of the design as a design under test. So we have some code that is only used for testing in the simulation phase to make sure that things are correct, and also have the ability to see the waveforms in the simulation phase. But then once we go to the actual design, we have the constraints given to this hardware implementation of the FPGA hardware software, which is the Altera Quartus Prime. And this tells us what is the area I want on this chip, what is the power budget, or what is the frequency I want. And then typically we can't optimize for everything. This will be like a Pareto optimization that is typically not possible. What happens in typical design is that we give part of these design criteria as constraint, and then we try to optimize only one of them or a combination. For example, area delay product, but giving one of them as a constraint. And the design under test is, again, part of we define a real construct, such as a built-in self-test that we use in testing of the chips to test this piece of design in logic. And once we go through the software that translates the System Verilog to a netlist, the netlist is actually this output of a synthesis. When we do behavioral synthesis, the algorithms go to the functional blocks, not necessarily the gates, but the functional blocks, such as ALUs, CPUs, and so on. In logic synthesis, we go and translate this into gate-level netlist representation of the design. And then physical design is something that goes one level further, because the logic synthesis can give us logic that you could implement with any fabric, with PLA, with FPGA, with ASIC. The physical design is actual physical implementation of this. And then the various ways how the netlist can be designed, for example, using a directed graph or directed acyclic graph if it's a combinational circuit, where we input outputs are coming into the gates. You could also have transistor level implementation of this. So synthesis of logic is really that compilation that you have seen in software. When we write a code, it gets compiled into a binary representation and gets you a binary that runs on the machine. Here, this is a gate level netlist, and this is typically going to a technology dependent format, because we should have an understanding at the high level of the design. Is this netlist going to be translated, for example, to an FPGA, to standard cell logic, or so on and so forth? The technology library is known by the size of the transistors in ASIC, and both logic level and gate level optimization are done during the synthesis level, and the constraints are typically the physical constraints, and they're given by the designer. The logic synthesis is really the translation, optimization, and mapping to a physical design. And the objectives is to minimize the performance in terms of area, power, or actually maximize the performance, but minimize these values to have an optimized performance, or a combination of these. And typically, we can do this in an iterative way, meaning that we get feedback from one set of synthesis, then we go and redo the synthesis or part of the synthesis to get an optimized solution. The synthesis flow for ASIC is on the front end pretty similar to Verilog that we use for FPGA, but the technology mapping and optimization is quite different, because here the technology is the standard cells that can move around. The interconnects between them is not just the switches that were defined previously. So that's a big difference between FPGA and ASIC. And the nice thing is many times the tools that we have at our hands can take care of both these things. So if you go into an ASIC design team, there are tools that are specifically designed for ASIC design flow, and those could be used in conjunction with System Verilog to have an optimized ASIC and compilation into standard cell libraries. Hopefully the knowledge of the System Verilog you learned from this course is super helpful in doing that as well. In last but not least, here I'm just putting some key points for FPGA versus ASIC comparison. The advantage of FPGA is that it has a lower time to market. We don't have to go through that fabrication. It has a much higher flexibility, reusability, and non-recurring engineering cost is higher here. The ASICs, it has that, the high volume production is because there is a lower cost per volume. Then it makes sense to make the mask or pay upfront because of that economy of scale for the mask. It has higher performance, lower power, lower area, but of course the disadvantage of ASIC is the non-flexibility, higher time to market, and non-recurring engineering cost that is happening here. And there are applications for both. In fact, FPGAs have been getting more and more market in the past 30 years that they've been introduced and getting popularity. And but there are still a number of applications that are using ASIC, and there is basically no replacement for one or the other. There is a market for both, and that's why both of them are very important to learn and use. In appendix, you could see more information about FPGA features and specifications.